I'm going to speak about application of remote sensing and open source tools for the analysis of biological characteristics of corn. At the beginning, our experiment was located on two locations in Bosnia, of course in Sarajevo and in Aleksandrovac, Banja Luka, and the picture shows you our experimental fields in Sarajevo within the Faculty of Agriculture and Food Science, located in Butvir, close to the airport. There we had in total 7 hectares, and we have there few experimental plots, orchards, greenhouses, laboratories, and classrooms for the students. We used the local hybrid of corn for experiment BL43, and the table shows some information about planting distance and some important dates from soil preparation to harvest in 2021 and 2022 of experiment. Also, we had 3 treatments. So one treatment was with full irrigation norm. It was around 30 millimeters, and half irrigation norm or deficit irrigation norm, it was 50 millimeters, and the plots without irrigation. So at the end, 3 plots of each treatment. Each plot was 20 by 20, and in total 3,600 square meters. As you can see, in 2021 and 2022, there is some differences, because in 2021, the first plots were with full irrigation, the second was with half and deficit, and the third was without irrigation. But in 2022, the first plots was half irrigation, the second one with full irrigation, and the third one without irrigation. When we are talking about irrigation norms, as I said before, for full irrigation 30 millimeters, and for half and deficit irrigation 50 millimeters. But you can see here on the figures the distribution of irrigation for each plot, for plots with full irrigation and with deficit irrigation. You can see in August and September that we gave less water in 2022 than in 2021. The main reason was the precipitation, because we had the double amount of precipitation in 2022 than in 2021, and the reference evapotranspiration was almost the same. So in total, in 2021, for full irrigation plots, we gave 360 millimeters, and for deficit irrigation plots, we gave 180 millimeters, and in 2022, as I said before, we gave less water than in 2021. And what about the yield that we got? According to Institute for Statistics of Bosnia and Herzegovina, you can see in the table the average dry grain yield of corn in the Federation of Bosnia and Herzegovina and in Canton Sarajevo. But with irrigation, we got much higher yield than its average. So in 2021, we got around 12 or 13 tons per hectare. In for full irrigation and half irrigation, and without irrigation around 4.5 tons per hectare. But in 2022, also we got higher yield on plots with full irrigation around 40 tons per hectare, and with depth irrigation around 12. Also, without irrigation, we got a little bit higher yield, not a little bit, almost double, of course, because of more precipitations in 2022. Now, I'm going to speak about using of remote sensing in agriculture. Probably someone knows what is remote sensing, but remote sensing is the process of detecting and monitoring some characteristics of an area by measuring reflected and by measuring its reflected radiation at the distance using some special multispectral cameras. So here you can see some organization and programs which are related to remote sensing. One of them is ESA, European Space Agency, that is intergovernmental organization for space exploration. So ESA providing many toolboxes, many useful toolboxes that we can use to analyze images from the satellites. For example, there is very useful software called ESA Snap, and within European Space Agency, there are one very ambitious Earth observation program to date, and within that program there is a mission called Sentinel-2 that systematically acquires optical imagery at high spatial resolution from 10 meters to 60 meters over the land. So I will give you some information about the Sentinel-2 mission. There are two satellites that operate together, Sentinel-2A and 2B. Sentinel-2A was launched in 2015, and Sentinel-2B was launched in 2017. Both of them has 13 multispectral bands. You can see the list on the picture, but the most important bands for us, for agriculture, are blue, green, red, NIR, and SWIR bands. Those two satellites are sitting every 10 days under the same viewing angles. So every 5 days we can have the picture of the same location, same target area of the land, and they have a special resolution of 10, 20, or 60 meters, and they have 290 kilometers field of view. Also, very important is that you can have that images from satellite totally free of charge, so the images are open access. Here you can see the website of Copernicus mission. So it's called Copernicus Open Access Hub. Only you need to be registered, and you can find the images from a specific date of your target area and download it totally free. So for our experiment, the sensing date was from 1st May to 20 November, so the vegetation period of corn. The main problem with these images was the clouds. So the Bosnia is a specific area, so during the year you can see many clouds in many days. So that is the problem for satellites to take images of the land. So we found 21 useful images in 2022 and 26 useful images in 2021, and download them. That images were analyzed by SSNAP software and also QGIS software. We use that images to calculate some vegetation indexes. So you can see here some basic information about vegetation indexes and the list of some of them. For us, few of them were important, and we calculated few of them. The first one is NDVI, so Normalized Difference Vegetation Index. This index is most widely used vegetation index for agriculture. That index quantifies vegetation by measuring the difference between near-infrared bands and red bands. So it ranges from -1 to +1, and it's a standardized way to measure vegetation health. So the higher values of this index means the healthier vegetation. You can see that on the picture. And also the equation how to calculate this index from satellite images. Now I'm going to show you a few pictures from the start of vegetation until the end of vegetation, how you can see here on the pictures the differences in NDVI values during the vegetation period. So the left images are images from 2021, and on the right side are images from 2022. The color close to the, I don't know which color, not the black, the orange or brown probably, means the lower values and almost without vegetation. But if you see the greenest pixels, that means very healthy vegetation and higher values of NDVI index. So I think first picture starts from 24th May in both years. So here you can see the differences and our plots. Keep in your mind that these photos are from different softwares. So in the photos from 2021 are from QGIS, and for 2022 are from SSNAP software. So maybe there is some differences in the colors. I will show you the picture during the vegetation period, how it changes. So you can see now it's much greenier. So for example, this is the date is 23rd July. So you can see here higher values of NDVI index for our corn. Also, next images are much greenier. So this is the middle season of growing corn, and this is this date is, I think, represent the top values of the vegetation health and the NDVI values. And after that, you can see the corn is finished with vegetation period, and you can see now the brown pixels. Here, in two tables and figures, you can see also some average values of NDVI indexes for each treatment, for full irrigation, half for deficit irrigation, without irrigation, with rain, and for plot with grass. And also in on figure, you can see a little bit difference between 2 years. Not too much, but a little. As you can see, most of them were higher in 2022 because of course, because of more precipitation. One of the reasons was more precipitation in 2022. Here are also the graphs. You can see the differences for both years, the differences between the treatments. So maybe the better values and better figures is in 2022, because you can see the higher values, the highest values are from full irrigated plots, a little bit lower from half for deficit irrigation, and again lower for plots without irrigation. And for grass, of course, it's much different than for corn. Also, this slide shows you few figures separated for each treatment for each year. So you can see the curved line from the beginning of vegetation until the end of vegetation for every treatment. Next vegetation index that we calculated was SAVI, soil adjusted vegetation index. So we used SAVI to correct the last one, NDVI index, for the influence of soil brightness in areas where vegetative cover is low. So it's used often in arid and semi-arid regions, and also it ranges from -1 to +1. And it is calculated as a ratio between red and near-infrared values with the soil brightness correction factor. We use that factor, the values for that factor 0.5 to accommodate most of the land cover type. And also you can see the equation how to calculate this index. And these are results of this index for 2022. Now we have also everything calculated from 2021, because we had some problems with satellite images for the first year, but now we solved it. But I will show you only the results from 2022. So the right figure shows you the average SAVI indexes, values of SAVI indexes. So the higher values are, of course, for the plots with full irrigation, and lower and lower until the grass. Also, the other figure shows you also the curved line from the beginning of vegetation until the end of values of SAVI index. Again, you can see the curved lines from the beginning until the end for each treatment for SAVI index. The third index that we calculated was leaf area index. So LAI is one of the most widely used measurements for describing plant canopy structure. So it's a ratio of one-sided leaf area per unit of ground area. So you can see that on the picture on the slide. The unit is square meter per square meter, and usually ranges from 1 to 6. So also you can see the equation how to calculate this index. The important things here is that we calculate this index on the ground. So we have the real values, and we calculate it from the satellite images also to see the difference in values. Here also you can see the average lie values for each treatment. Also for full irrigation plots are the highest values, and etc. And also the curve line from the beginning until the end of the vegetation period of these units. On these figures, you can see the difference between values from the ground, real values, and the values calculated from the satellite. In every case, during the season, there were lower values calculated from the satellite than real values. But again, the curve lines are very similar for both measurements. And very important for leaf area index is to calculate linear regression and correlation coefficient between measurements from the ground and from the satellite. As you can see, we got R square almost 0.9, which means it's a very high correlation between these two variables for full irrigated plots and half irrigated plots, and for plots without irrigation also 0.78. That means also very good correlation between two variables. And at the end, for us, very important was to calculate crop coefficient for the maize, for the corn. The crop coefficient is properties of the plant that used in precision evapotranspiration, and it is the function of different variables of crop type varieties, phenology, plant density, soil water content status, irrigation methods, etc. And there are two approaches to calculate crop coefficient, single approach and dual approach. Single crop coefficient integrate the effects of both of crop transpiration and soil evaporation. But dual approach is the solution that consists splitting crop coefficient into two separate coefficients. So one of crop transpiration called the basal crop coefficient, and one for the soil evapotranspiration. So we choose to calculate basal crop coefficient from the satellite images. This coefficient, defined as the ratio of crop evapotranspiration over the reference evapotranspiration when the soil surface is totally dry, and this coefficient varies during the growing period, and it represents in the crop coefficient curve that you can see on the pictures. And also there are 4 growing stages of maize and 3 values which describe the crop coefficient curve. So we have initial phase, the development phase, mid-season phase, and late season phase, and 3 values, KCB initial, KCB mid-season, and KCB end. So we calculate this crop coefficient using the QGIS software, and also use this equation. There are many equations, but we use this one. We thought that this one is very useful and possible to calculate for our case, and also reference values for some values from the equation. You can see in the table for corn, of course. And we calculate this crop coefficient for our case, and you can see here for different treatments. Again, the curve line of the crop coefficient, basal crop coefficient values from the beginning until the end of season. And you can see here similar curve as you saw before on the picture for three treatments, but for the grass it's not the same, of course, because it's not corn. And now the most important is the values of three crop coefficient, basal crop coefficient, KCB initial, KCB mid-season, and KCB end. And also we measured the duration of this growing stage on the field for each treatment, and you can see how many days are every growing stage for a full irrigation plot, and we have also reference values for KCB values for corn. We got the closest values that we can got. So you can see KCB for mid-season is the lowest one. Of course, not the lowest values, but that represent the highest values during the vegetation period. But there are significant difference between reference and observed values for corn. And we got the maximum values of basal crop coefficient for full irrigated plot around 0.84, and the lowest one 0.22 for KCB initial phase. For half or deficit irrigation plots, also we measured everything similar, and we got very similar values of basal crop coefficient. There is no significant difference between full irrigated plots and deficit irrigated plots, so you can see almost the same values for KCB. And for plots without irrigation, we got a little bit different values, lower values of course. The highest value of KCB was 0.72 in mid-season, and the lowest values was also 0.22. But for plots without irrigation, the duration of this growing stage are a little bit different than for fully irrigated plots and deficit irrigated plots. And that's it. If you have some questions, I'm here to listen to you and answer if I can.
Thank you.
Please, Julio.
Yeah, just one question. Do you think that the size of your experiment affects the quality of the result from the satellite images? Because I think that the size of the single parcel of land was about 4 pixels wide. So do you think that making a bigger experiment would solve some challenges that you have?
Of course, you are right, because we don't have too much space, too big areas at our experimental plots to do it how we should do it. But we do it with our small plots. I think it was 6 pixels per one small plot. So 12 pixels for each treatment. That's not enough, for sure. But we didn't have much space to do it on the bigger plots. But for sure, for this type of analysis, it's much better to have the bigger plots with few hundreds pixels. But unfortunately, we don't have it, and we tried to do something with our experimental fields and calculate what we can calculate.